Good evening or good afternoon, YouTube. So today we're going to be talking about this new study here. Genetic ancestry and social race are nearly interchangeable. That's the title by the not Dr. Emil. And the study is in OpenPsych, because where else would you put these things these days? There you can either do OpenPsych or you can do Mankind Quarterly, and OpenPsych is cooler because we love open science. And also it's faster because it doesn't use this the quarterly stuff. It's also open access, which is nice, right? Anyway, so the thing normally goes is that it has been claimed that social race, which is either self-reported, parent-reported, or some like interviewer kind of reported race or ethnic grouping of some person, and an actual genetic ancestry, which you can test with 23andMe or any other genetic data, that these are at best weakly related, or even maybe not related at all, or they have a complicated relationships, or some kind of claim like this. And essentially, I looked through data sets that you can also download and redo this or do it some other way. And the ping dataset. We previously used this dataset to study ancestry and IQs and stuff, and so that's the one with for the first paper in 2019. Anyway, you can download this dataset also and play around with it, or you can just listen to this video. To not do too many spoilers, obviously the results of trying models that predict social race from genetic ancestry and the other way around, these accuracies were always very high. Hence the title of this paper, so I guess I'm not spoiling too much there since it's literally the title. For those wondering about which kind of claim we're talking about, I'm talking about books like these, or in the right situation, it's the cover of the National Geographic, black and white, with these dizygotic twins, and you can see within family you can have a lot of variation, and to some people who are bad with statistics, this may tell them very much. We also have these kind of typical academic books. You have the Sussman book, The Myth of Race, and the almost same title book by Graves. I think he's some kind of anthropologist. These kind of books will usually be by anthropologists or philosophers, depending on whether they're going to be like more oscurantism or just more stupid, in the same order. So some quotes from this. Overall, this work demonstrates, from a biological, systematic, and evolutionary taxonomical perspective, human races, continental groups, or clusters have no natural meaning or objective biological reality. This is kind of typical claim you can gain. Or what about this one? Human ancestry correlates with language and reveals that race is not an objective genomic classifier. Not objective genomic classifier. What is even that? Finally, results demonstrate consensus that there are no human biological races, and recognition that race exists as lived social experiences that can have important effects on health. You would not be surprised to find this in 2016 from a survey of American anthropologists, right? There you can find thousands of these quotes. I just picked these ones basically at random to illustrate. And of course, on this channel, we believe in quantification, and essentially science is very weak until you start quantifying things. Okay, I made this poster with Lord Kelvin, and his famous quote about knowledge, which I even had a printed copy somewhere, but not right here. So where does this data come from? How can it be public? Well, it all goes back to 2015, where we had this Poverty Shrinks the Brain, according to Nature News, and essentially it's a study. The ping study, the dataset, and if you do this study and you use parental income, you can see that the kids with poor parents have smaller brains, and of course they interpret this as being causal, although this would maybe just be explained by kids with parents that are poor are kids that have dumb parents, and dumb parents have smaller brains, and so do their children for very genetic reasons. And anyway, so this as you can see with the alt metric, this study was extremely popular on Twitter and all this stuff. Finally, we proved poverty shrinks the brain and so on. And the weird thing about this study is that they actually attached the data here. They attached the data to the figures, which is a bit weird. And it's the Noble study that James Thompson also had a blog debate with her about, trying to explain to her that genetic confounding is something you might want to look into, sis. But I guess she didn't, since instead she ignored this and then got a big lucrative grant to do more useless research. But hopefully maybe she can fund some more data that they will share. But that's just our hopes. Anyway, so you can go to the website and you can download these data that includes almost all the data in this video. The remaining data, I think it got someone gave it to me. I forgot the origin. Definitions in this case. Race is essentially a genetic cluster. It's a kind of a far extended family in, to quote kind of Steve Saylor approach. Usually, historically, these were identified based on visual cues, and you can obviously use skin color, which is not perfect because some Indians are also black, and so are the Aborigines, and so that won't work alone. But skin color, along with say frizzly hair and nose width and some other things, and then obviously you can tell Africans apart from the South Indians, which are shorter and I think have not wide noses, and the Aborigines, I don't actually know how you tell these apart, but I'm sure some random bones and stuff will tell them apart. Ancestry is the modern current euphemism. Sometimes they call it biogeographical ancestry to kind of, or continental ancestry to kind of refer to the continent's ancestry. Whatever the case, it's actually the same as above. It's just a currently correct measure. But you can also find some papers that attack this. And of course, in a few years, I'm sure we'll have another euphemism. And social race or ethnicity, these are the racial classifications of some person as judged by the same person, someone else, or other. So these are the ones that go on like the government censuses. And if you just kind of ask people to describe, look, he's an Italian person. So, Italian is also ancestry, and if you were to look at Italian from a genetic perspective, you would see, the North Italian cluster and the South Italian cluster, and I think those people on the island that have weird mixture. Whatever the case exactly, you would get something like this. So these are the definitions of the terms as used in this video. Race and ancestry, these are essentially the same. But social race, which is the one we're talking about in this paper, that's the one they use in actual surveys. And so the real question of this paper, and as we went over, is that how strong are the statistical associations between social race or races and genetic ancestry? And it's a question you can quantify, and quantification makes Kelvin happy, so let's do that. That said, let's look at the data. I've decided to simplify it in one situation and keep the full complexity in the other. And this data set has some 1,400 people or so. And if you look here at this table, it shows the overview of these people. It's 40% just pure white, pure European origin, almost pure. And then we have a bunch of other people, and then we have this remainder category. And the remainder category is everybody who chose a different combination of these. And what do you mean different combination? Well, every person or their parent, probably the mother, was asked to racially categorize themselves or their child. And you had, I think, eight options to pick between, something like that. And you can pick different ones, or you can just pick one. And so essentially you can get a kind of combination. So for instance, white and Hispanic, where people who pick both Hispanic and white. So these will be kind of the more European Hispanics, and the ones who just picked Hispanic, there may be slightly more higher in Amerindian ancestry, or maybe they're just it's kind of arbitrary to some extent. African Americans are those, blacks in the US, and remainder are people who picked like even more complicated combinations, or just combinations that didn't have many people in this data set. And so here we see, for instance, there's like 32 people picked Pacific Islander, Asian, and white. I guess these are like people from Hawaii with mixed ancestry. There are also some people who just picked Pacific Islander alone. And so these are more pure, probably, but there was fewer than 20 of them, and so it's a bit difficult to model when there's so few. So I put all these remaining options in the remainder category, which is obviously a very broad one that would be kind of difficult to predict, because you're essentially not predicting anything particular, except you're not a member of any of these other groups. So that's a data limitation, and if you had a larger data set, obviously you could have a more sensible classification. But in the first part of the study, we're looking just at the whites, the African Americans, and the African American whites down here, these 25 mixed people. And so this is half the sample, and that's gives us an easier situation where we can talk about things. So statistically speaking, we can go both ways, and you can predict social race, the combination as talked before, from genetic ancestry, or you can predict genetic ancestry from social race. You need different models for this. And in the simple situation where you just need to predict social race, you can just use ordinal or logistic regression, since in the simple situation all you have are three groups. You have the whites, the people who are both mixed black-white, and then you just have the blacks. So you only have three categories and they come in order. So in this case you have ordinal regression or ordinal logistic regression. And if you instead want to predict all these categories precisely, you have to use essentially what's called a multinomial regression, which is a fancy word for saying that you have many groups and each of them cannot be put in any particular order. That's the nominal part, and you just want to predict which is the most likely one. This is the standard regression approach. You can of course use random forest or something else if you want to do any kind of other classifier. In this paper I've kept it simple, but I've actually also tried these more fancy methods and they didn't really produce better results, maybe because the sample size is too small for them to really show their superiority. Anyway, so we're sticking to the simple models here. Predicting genetic ancestry from social race, in the first situation it's very easy, because when you are dealing only with African Americans or blacks and white people, these only have two ancestry components, and these are negatively correlated at -0.1 or -1. So you essentially only have one non-redundant one. So there's only one outcome, and so you just need chat linear regression, who I've depicted over here. And so that stuff is very easy. In the, I guess it should say simple situation here. I forgot about that. We'll put it here just now. In the complex situation, you have a lot of outcomes. So you have many ancestries you want to predict at the same time, and only one of these are redundant. So if you can see it for yourself, if you have a few different ancestries, then let's say you have people with three ancestries. So if I give you two of them, you know the remainder one must be whatever is left over from 100%, and so the last one is redundant. So you only have like two free ones. And when you have multiple outcomes like this that are all that all sum to one, so it's a composite or compositional data, then you use this thing called the Lit regression, which I think we'll get to more here. Anyway, so that's the thing. So here's how it goes with the simple situation. The black one here is the black people. That's the probability that the model thinks you are black. As you can see, the probabilities here, and the green one is the mixed one, and the red one over here is the white people. And down here on the x-axis we have the African ancestry, and so you can see essentially that people with, say, below 10% or so, this is like 12.5, so this 10% is roughly here. These people are essentially 100% chance of being predicted to be Europeans or white, and that's the model essentially gets it wrong almost never. The tricky part comes with these people who are both, as distinguishing them from these and from these is tricky. You can see basically the probabilities are overlapping here, and that's why it's a bit difficult. It's overlapping in a not too nice way. Nevertheless, if you look at the actual prediction from the model, you have this thing called a confusion matrix, and what you see is the true values, and these are the true values because these are people who filled out some questionnaire. And as we know, people filling out questionnaires are not always entirely honest, or they sometimes just make mistakes. And so we have a kind of lizard man's constant issue. What we see is that among the 497 people who are or were chosen by their parents to be white only, the model predicted 496 of them, that is all except one, to be white. So the accuracy is absurdly high for whites. It's this value, and 99.8%. You can do the same exercise for these and you'll see it's not so impressive. It's like 60%, and for the blacks alone it's also very high, 97.7%. Of the three, there are 130 of them here, and the three errors are all predicted to be in the green one instead of the blue one. And then so the only really kind of big error with this model is this one person here who claims to be white but essentially has very far African ancestry, or a very high African ancestry, and so maybe it's someone who filled out the survey wrong, or maybe it's one of these, it's kind of a reverse, whatever that white woman was called, who pretend to be black. I forgot what she's called. It's kind of a reverse case of this, since it's someone who claims to be white but actually is African. Anyway, overall you can really see that these the accuracies are very high. Overall, it's 98% in total. The curve under the area under the curve is extremely high, 99.4, and the pseudo R squared is 93. And if you know anything about statistics and reading other papers, you know that these values are absurdly high for data dealing with individuals, and so it's not too surprising from these results. Moving on, we have the simple situation again, but we're going the other way this time. So this time we just want to predict genetic ancestry from social race, and I plotted using these violin plots that apparently some people are not familiar with. And what you really get is that if you get the African ancestry here on the y-axis, you can kind of see the distribution. So what you see for the white people down here is that essentially everybody has below 10% African ancestry, or maybe even below 5. There is like one person who was over here somewhere, right? That's why this kind of line is here. I guess he's there. That's why it's made like this, or she. For the people who are mixed, so these are only 25 people, so that's why it's a bit weird looking. And so these are kind of having a mean of I don't know, 40% or so. That's also the mean you saw here, so 40 something percent. So this could be because the people who call themselves mixed are people who are first generation mix of an African American and a pure white person, and the average African American is roughly 80% African, and the average European is like 1%. So if you take the average of these two, it will be roughly 40, and that's what you get for people who said they were both. So maybe this is just the children of people who are a recent mix of this. I mean, the African Americans are already mixed, but they've kind of broken off and then mating mostly among themselves after the initial mixing, and now they're mixing again, and so this recent remixing, I guess we could call it, they would then on this explanation be roughly 40%. So that kind of explains this value here. We don't know exactly because this data set doesn't give you the race of the parents, and you'd have to try to guess from the Y chromosome and the X chromosomes insofar as possible. We didn't try this. And the blacks over here, the African Americans, they have a mean. You can see the mode is where it bulges out the most. The mode is here, and the mode then will be like 90% or something like this, because this is 25 between, so it will be 87, 88 or something. It's here. That's their mean. But you can see there's a long tail here, and so if you take the mode, and if you take the mean from this long tail, you will get somewhere around here, right? So you see essentially that the ancestry of the African percentage of whites and blacks doesn't overlap except for this one person who was over here. So the model telling these people apart would have 100% accuracy aside from this one person. This group is hard to tell apart because these down here, they overlap with the whites. So there are some people who are essentially not African, but nevertheless they identify as both white and black, and these are the people down here. And there are some people who are up here. They're essentially very African, but they have like they're essentially slightly less African, slightly more African than the average African American, and yet they also identify as white. So whatever the case, you don't know about these people, but you can see the biggest cluster is down here in this area, around 40. So again, the model is extremely good when you look at the statistics. It's just a linear regression. So here you just predict African ancestry from these three groups, and you get a model with this adjusted R square of 95.5. So 95.5% of the data of the variation is explained by just asking people these racial questions. It's an extremely good model, right? Moving on to the special case, it gets more complicated. Here we have all these people, and as we went over before, we're trying to predict the exact category that people are in here, including this remainder category that's kind of difficult. And so here we're trying to do that, and you can do it here. Here's the accuracies for each group, and so these are the percentages of each groups and the sizes that were correctly classified. And so you can see the 32 people who were Pacific, Islander, Asian, and white, none of them were correctly classified because the model just couldn't figure out to predict these people with this strange ancestry mix. And the remainder category was also not very impressive at 56%. Here, important to keep to mind is that these values should be seen in light of what the prior is. And we had the same situation over here, where we only had 59% or roughly 60% for the mixed people. But if you then remember that among the 700 people or so, only, what can we see here? 22 of these are actually mixed. So you're trying to predict the correct class for these 22 people out of whatever the 700 people in total are. You can see this is very difficult because the prior is quite low. So the model somehow still getting to 60% is actually kind of impressive. You have the same situation with some of these groups. There's only 29 of these people. It gets to the Hispanic African Americans, so these will be kind of African Americans that have intermated with the Hispanics, and now they have some kind of mixed genome based on a combination of this. And the model, attains not very convincing accuracy of 35% for these 30 people. But overall, you can see the model is quite good. The Asians, it's pretty good. African Americans is pretty good, and of course, white people pretty good. And so once you can calculate this overall area under the curve of this model, there's a multivariate version or a multinomial version of this, and you get this value area curve of 92.5, which is still very good. It's actually, so we'll see, it's actually on par with like medical stuff. And for those who are interested in the confusion matrix that we had before, it is here. But as you can see, it's a bit difficult to read, and we won't go over it here, but you can pause the video and kind of look into it. Okay, we can take one case. If you're looking at the people who say they're African American, you can see the model predicted 82% of them to be African American, 4% of them to be white. You can read the output of the R from the study and look into more details. And the Lit regression, as I went over before, it's when you have data that are compositional, which is to say every row sums to 1, so you have some kind of composition of something. Often it's used in geology, where they have different kinds of dirt, basically, and in the ground, and you say it's 20% 20% this kind of dirt, 20% this other kind, and 0.1% gold or whatever, and this all sums to 1, and you want to predict these things. And so why do we use this instead of just standard linear regression is that the standard linear regression doesn't understand that numbers cannot be out of this bounds, and so they don't have to sum to 1 either. And so because of these two problems, you can still use linear regression, the multivariate version, but it's just that your predictions might actually be somewhat nonsensical. Like some person might be predicted to be, minus European ancestry or something like this, and you'd have to maybe round the numbers and then, or not round them, like put them at least to 0 within bounds, and then re-standardize them to 1 to 0, and this will probably give you some kind of bias. It's done with some data transformation, but you can basically read this paper here that we're not going to look into too much, but it's this paper, and it's in some ecology stuff, and it will give you kind of semi-intuitive explanation of how this thing works. Genetic data is also compositional, since everybody's ancestry sums to 100% of whatever it is they have, and it's named after this guy. Let's do the other situation then. Before we looked at predicting, in this one, we predicted social race from genetic ancestries, and here we're going to do the other way around. So here we have these 6 ancestries that are in this study, and we want to predict them from the social races that people have picked. And you do this in the direct Lit regression, and it gives you these the predicted values are on the x-axis, and the y is the true ones. And so what you see is essentially you see these nice kind of lines here for the ones you can do it with. Central Asian, you see there's not much there, and it's because there's the Central Asian ancestry in this data set, as you can see, is all it goes from there to there, but the model really didn't predict any of it because there's too few of these Central Asians for it to kind of figure it out, apparently. And so Oceanian, that's some of these Pacific Islander people, yes, that too. Anyway, if you are to, instead of looking at this and not being too satisfied, you look at the actual values, which are the ones everybody else is reporting for their studies, then we see these values. And the problem is that direct Lit regression doesn't give you 1 R squared. It gives you all these predictions, and you're kind of left wondering what is the overall R square. But there are 6 sets of predictions and 6 sets of true values, and of course you can correlate each individually. And if you do that, you get these values. So you can see the model was pretty good at predicting African ancestry. 92 is a correlation between predicted and true. It's this one up here. It's very good. It's pretty good for East Asian also, 86. And for European, 88. It's all still pretty good. Oceanian, slightly less impressive. It's terrible for Central Asian, as we were talking about. But overall, it's pretty good. And if you are to just take all these vectors and put them after one another to get a kind of overall correlation, it's this one, 92, and which is very good. And that, of course, corresponds to an R squared of 85. The relationship between these two is that you simply just square this value, you get this one, or take the square root of this to get this one. So that's why it's obvious what the values are. So overall, according to numerical indexes that everybody else uses, these models are very good. So that's what the questions are. Emil, I see some not quite perfect results. That's right. However, I've dug up this reference guide. It's actually difficult to find a guide for area under the curve interpretation. Everybody just kind of uses some kind of intuitive one, but I found this book about logistic regression, and it actually does give a guideline here, and RSCs, these receiver something, whatever, I forgot what it's called, receiver operation curve, whatever it exactly means. Essentially, you 0.5, that's just average, and this will basically means your model has no accuracy. So 0.5 is 0 if you are to transfer or intuitively think about it, and you want 1 is perfect. And so if you go across up, you can see you can get like acceptable discrimination. This level of accuracy down here, that's roughly where genetic models are right now for predicting, say, breast cancer or something like this. They're not that good. But they're sometimes acceptable, sometimes they're even below 0.7. Above 0.9, I've been reading some medical papers that I won't go into here, but 0.9 or more is that's a really good medical test. Let's say you do kind of a blood test that has it's looking for a specific protein that is almost a guarantee for having an illness, then the RRC or the area under the curve will be over here. And so it's considered outstanding discrimination. And if you were to think back of all the numbers we reported, indeed all of them were actually above 0.9. So they are all outstanding discriminators, or to be a little based. But what it really means is that the data are very well able to tell apart these underlying groups. So that's really what you get from looking at actual guidelines from an actual statistics textbook, is that it shows that these kind of values here, we have 92.5, and the one up here is 99.4. It's absurdly good, right? These values are all far beyond what you can mostly get in social science. After all, remember, most of social science, they cannot even replicate studies. And so to not only replicate, this is not the first time we did this, to not only replicate, but also get extremely high accuracies that puts it really in a different league to most of the mostly false stuff. So this is all not very surprising. You might say it's kind of obvious. Yes, it is kind of obvious, and indeed should not really be questioned by someone who has looked into these things. But nevertheless, we have these people. We have the Adam Rutherford over here. He's the Dr. Adam on Twitter, or is it PhD Adam? He's one of these credentialist people, and he's has this book that's kind of popular and got some, I'm sure, very good reviews in The Guardian or whatever, How to Argue with the Racist. And we have this Sussman here, who is also promoting his whatever book, The Myth of Race. And so these people are, they're quite popular, and they say things that are wildly contrary to facts and easily verifiable statistics. But nevertheless, it's popular. So of course, here on the channel, we are attacking people who say popular but false things. And that's really what what my science work is about. If you want to do more of this science work, of course, I've been Substack maxing recently, and here's the current offerings, and hopefully you're gonna be looking like that, and going there and then clicking the subscribe button, blah blah blah, more money for me, more science for you, and with that said, I hope you have a nice day.